Okay, so this is the question on your quiz here. It's y equals x squared over x squared plus 3. And A says find the domain. So that is all allowable values for x. And what you want to see here is that if x equals 0 in the numerator, that's okay. X in the numerator is okay. 0 in the numerator is okay. 0 in the denominator is bad. But if we had something like, 0 here, that's still a 3, so it's 0 over 3, that's okay. The problem would be is if x squared plus 3, if that were to equal 0 anywhere, then we got a problem. So if we try to solve for x, we get this, and then we try and take a square root. Look what we have to do. Square root negative 3. You cannot do this. So that means that there's no x value that causes this to be 3 or to be 0. And x squared cannot ever be a negative number. So it would have to be negative 3 in order for this to be 0. So all in all, that means that there's no restrictions on the domain. So domain is all real numbers of x are possible. Okay? Hey, questions? That one? Okay. All right, just stop me if you have questions. I'll try and stop at the end of each one too. So B, now intercepts, right? B is intercepts. So if you let y equal 0, like I did over here, and then you solve for x, well, when this whole irrational is 0, when the numerator is 0, and I just realized I put cube there. So x cubed equals 0, well, that's only 0 when x equals 0. So we have x equals 0 is our intercept is 0, 0. Okay, 0, 0. And so if 0, 0 is an intercept, then the y-intercept has to be 0, 0 as well. Question?
X cubed.
Yeah, I didn't mean to write that, sorry. Actually, that should be squared, sorry. I think this original question, I was going to make it x cubed, but then I changed it. So, yeah, some of the stuff I didn't erase everything. But, yeah. So if x equals 0, y equals 0, so the x-intercept, and technically 0, 0 is the x-intercept, and 0, 0 is the y-intercept as well. I like the points. Technically, you should be using points. Some textbooks and some profs might say, oh, if you say x-intercept is equal to 0, I get it. That's an x equals 0, and obviously y is 0. Whatever. So you might get away with that, but usually the points are best. And hope you understand that if this is an x-intercept, this is also the y-intercept as well, because you can only have one y-intercept, so that is the y-intercept. So is B good then?
Yeah.
We're taking care of B? All right, excellent. So C, symmetry. All right, so symmetry, what we want to do is we want to choose a positive value for x and then the negative version of that value, that same value, and see what the evaluation looks like. So if I chose negative 1 and 1, so if you put negative 1 in, you get positive 1 over 4. This is just for example. You can choose any number. And then when I put the positive version in there, I still get the same, which means that this is an even function. Therefore, there's symmetry about the y-axis. Think of a parabola. This is not a parabola, but think of a parabola, right? That's y equals x squared. This would be x squared plus maybe 3 or something. But think about that. Because it's an even function, you put positive 1, negative 1 in there, you still get the same answer. A parabola is even about what? The x-axis, not necessarily about the origin. If it was an odd function, your symmetry is about the origin, okay? All right, so D, let's take a look at D. We want to find a horizontal asymptote, okay? Horizontal, and let's see if there's a vertical asymptote as well. So horizontal asymptote, you basically find out what happens to this function right here as x approaches infinity. So you take the limit of this function as x approaches infinity. You don't have, obviously you're sketching this, so you don't have a graphing calculator. If you wanted to test points individually, you probably could, right? If you wanted to take like 1,000 and put that in for x and see what the value is, and then take 1,000,000 and actually literally put it in for x, you could totally do that. But the way that you actually can solve this by using this limit property, right? The limit as x approaches infinity of 1 over x equals 0. Remember that one? So that's the one you want to use. So if we can divide everything by the largest exponent of x, so we'll do every term divided by x squared, this simplifies into this over here. And then as x approaches infinity, 1 does not change, that stays as 1. As x approaches infinity, 1 does not change, that always stays at 1 because there's no x involved. And then as x approaches infinity here, this approaches 0. So we end up with 1 over 1 plus 0, which is just 1. So horizontal asymptote of 1. You good with that? Okay. Did you do it this way or did you do it a different way?
Oh, I did.
You did it that way? Okay. There is other ways to do it. Like I say, you could just choose numbers. If I chose 1,000,000 and put 1,000,000 in here, it would be like 1,000,000 divided by 1,000,003. Wow, that's 0.99999, right? You know what I mean? So the larger numbers, you're just going to get 0.999999. That's pretty much 1. So, all right. So let's move to E. Now, I don't have it in front of me. E is intervals of increase and decrease, I believe. Is that right?
Yeah.
Yes. Okay, so this is where we do need to find the derivative, and it was mentioned earlier that maybe a derivative of a rational function can get a bit tricky. So let's do that. Remember that y equals x squared over x squared plus 3. So our derivative is going to be, we have to use the quotient rule here, right? So the derivative of the top is 2x times the bottom minus, it's always minus, you think of division and you kind of think of minus. Multiplication is kind of like addition to me. And that's mainly because of maybe the exponent laws. Like if this one, if you're multiplying, that's the same as adding those exponents, right? And if you're dividing, that's the same as subtracting. Did I say adding? Yeah, subtracting the exponent. So that's what I think of when I think of quotient rule. It's dividing. This is always going to be a minus. So derivative of the top times the bottom minus the top times the derivative of the bottom, which is simply just 2x there, it looks like, plus 0, right? Divided by the bottom squared. So I'm going to go x squared plus 3. And do you know what? We're not going to expand that out. Leave it in factors just in case you have a factor you can divide out or whatever. So that's always good. All right, so y prime. Okay, the top though, good idea to expand this out because if there's any like terms to add, I think that would be a great idea. So I've got 2x cubed plus 6x when I expand that out, minus, this is going to be a single term of 2x cubed. Oh, that's actually wonderful. Don't forget about the bottom. Why is that so wonderful? Well, because the 2x cubed terms are going to go, right? We got a positive and a negative. Does that make sense? So now I have a bit of a simplified version here of the derivative is just 6x over this one. So now would be a good time, because we're trying to find intervals of increase and decrease, that is the sign analysis, right? So find the derivative, get it into factors, and then do sign analysis. So sign analysis would include this elongated L where the bottom is a number line. And you place all the factors. So we have 6x as a factor. You place that on the side of this elongated L here. And I'm going to place these factors. So this is x squared plus 3 all squared. Now, you certainly can do this, write each one individually. I would encourage that. But you can also, at some point, you're going to notice that, hey, I have a quantity in here that is squared. You see that? So no matter what that is inside, this value on the bottom is always positive. Do you see that? It's always positive because it's a value squared. There's no signs outside. You're not adding anything. You're not, nothing. You're multiplying by negative. So you could split this up, or you could just go, hey, I understand that this right here is actually positive everywhere. So that one's actually pretty easy, isn't it? Just a positive everywhere. So that's a good shortcut there for you to notice. And then 6x is obviously it's going to be 0 at 0. And then when x is less than 0, this is going to be negative. When x is greater than 0, 6x will be positive. So that's your sign analysis. Under here, we have f prime of x. It would be negative, 0, and positive. Okay. So I'm going to pause there. Are we okay with the sign analysis and stuff like that? Yeah? So intervals of increase, decrease is derivative and then sign analysis with the factors. So this means that we have, tangent lines that are negative here, okay? Now I have a tangent line that's 0. I have a tangent lines that are all positive there. So you can see too that this is going to be a minimum, which we're going to answer the next question using this. And it's decreasing because of negative tangent lines. It's got to be decreasing. So decreasing from negative infinity to 0. A small note as well, I saw in one of your papers that one of you did this, square bracket by infinity. We don't want to do that because we can't technically include infinity in any of our intervals, okay? So I won't name any names, but we want to make sure when you have infinity like that, don't use a square bracket because that would include the actual value there, which we can't really include a number of infinity. There's no actual number that's infinity. It sort of just means, going that way forever. So it has to be round brackets technically. And then increasing, okay, on the interval, 0 to positive infinity, again, round brackets there. And we wouldn't square this bracket either because technically it doesn't make sense to say that it's increasing at 0 itself because that's the point where it flips. So you should use round brackets there as well. And I'm okay with these abbreviations here. And check with, if you're watching this video, check with your teacher to see if that's okay, but it's fine with me. Okay, so the next, that's good for E, right? That's our answer for E there. Okay. So F is it local max and min now? Okay. So according to this sign analysis here, right, the derivatives go from negative through 0 to positive. So that represents a local what? What is this point here at 0? It's a local, yeah, minimum, right on. So we have a local min at x equals 0. Now, technically you should name the y value as well. So this is what I prefer you to do. F of 0 equals, and then you put the x into the original function to actually get the point. So we should focus on points technically. So again, that's, 0 is what? 0, 0. That's an x-intercept. So f of 0 equals 0. Okay. Now what about the local max? Any local max that we can? No, there is no local max because the sign doesn't change again. If this went to 0 and a negative again, hey, then we would have, right? We would have a local max here because there'd be negative, 0, positive. But that doesn't happen. So because we don't have that happen, there's no local max. And you should say that, no local max. If you didn't say that, just left it like this, then I might think, oh, you don't know. You know what I mean? So go ahead and say that, no local max, and it'll be good. Okay, any questions at this point? All right. So we're getting close here. G is concavity and points of inflection. So arguably, this might be the toughest part of the whole question. I don't know, but we have to find the second derivative for concavity, right? Because where the second derivative is positive, we have concave up. And then where it's negative, we have concave down. And where the second derivative is 0, that's the point that it changes concavity. So let's go ahead and let's take the first derivative, right? 6x. So y prime is 6x on top, and then what do we have? X squared plus 3 squared on the bottom. So let's go from here and take the derivative of the first derivative. So the second derivative is derivative of the top, which is 6 times the bottom, minus, so quotient rule again, the top times the derivative of the bottom. Okay, so the derivative of the bottom, we got to use chain rule here. So we're going to have 2 times x squared plus 3, and then 2 minus 1 is just 1, so that's great. And then chain rule multiplied by, so we do power rule and chain rule in finding the derivative here. So now multiplied by 2x, which is the derivative of the inside. Okay. So that's maybe the trickiest part there, just keeping track of that. Now I'll put a secondary set of brackets there because we got to remember we're subtracting. This is going to be multiple terms when we multiply this out, right? There's going to be a little bit going on here, so we got to be careful. This is going to be x squared plus 3, all squared. Okay. Now, when you look at this, before you just go and expand everything, okay, and gather all your like terms, what you want to notice is this. You want to notice that, hey, you have a common factor in the top, every term in the top, like, so this is one big term, okay, that's one big kind of entity. We have a subtraction, and then we have more multiplication. So those are two separate groupings, and I have a common factor in both of those and in the bottom. So I'm going to be able to remove that common factor. Think about it this way. If I factor a common factor out at the top and bring it over here, then I can eliminate it with one of the factors on the bottom. Okay? Now, I think I didn't square this yet. Okay, so this is actually the bottom squared, so that's going to be a 4. All right? I saw some of you moving uncomfortably in your seats, so that usually tells me I've done something wrong, or you're having questions about something. So is that what you were moving uncomfortably for? Or must you be excused to go to the washroom? No? Okay, all right, I understand. So yes, that is to the power of 4. Is everything good there? Okay, all right. So what that means is this. I'm going to take one of these out. That's going to be 6 times x squared plus 3. This 6 times 2 times 2x, I can put all together. So what's that going to be? 6 times 2 is 12 times 2 is 24 times x is 24x squared. And this is going to be gone as well. So that's just simplifies to that. And on the bottom, I have now x squared plus 3 cubed. So that helps a little bit, definitely. And I definitely see that there's an x squared if I multiply this in that can combine with this x squared term. So I will now expand. And now this 6x squared minus 24x squared is going to be what, negative 18x squared? So negative 18x squared plus 18. And yeah, that's going to be able to be factored out if we want. You can take out a negative 18, I guess, if you want. X squared minus 1. Okay, that's one way you can do it. You could also have a positive 18 here and then have 1 minus x squared in there. That's okay too if you had that. So it looks like we all have factors here now. So let's do a unit analysis. Sign analysis with these factors. Negative 18 is going to be 1. And yeah, it's important to put that because remember that provides a negative sign all the way across. So we do need to put that negative 18. If it was a positive number, arguably you could leave it out, right? Because it's just positive, but it's negative, so I have to include that. Now, x squared minus 1, you could factor this further to x plus 1 and x minus 1, right? That's a difference of squares. So technically, we could do that, and I think I might do that. And just maybe be a little simpler. This one here, x squared plus 3 all cubed. So again, if you look carefully at this, you see x squared plus 3, that's going to be positive all the time because we have a positive number, a squared number, and then we're adding to it. You see that? So this is always going to be positive. That means if we cube it, this whole thing is always going to be positive. So you can use a little bit of intuition there and save yourself some hassle. So x squared plus 3 cubed, that's going to be positive everywhere. And it's never going to be 0 either. Do you know why? Because x squared plus 3 will never be equal to 0. And I think, did we talk about that already earlier in this question? Yeah. Yeah. Okay, so that's going to be positive everywhere. Now, it's just these two guys. So at negative 1, we're going to have a 0 for this one. And it's going to be negative where numbers are less than negative 1. It's going to be positive on this side. And if you're unsure about that, just test some numbers. So here I know that positive 1 for x, positive 1 is going to be 0. And if I don't know what sign goes on the left, think of a number that's less than 1, like 0. 0 minus 1 is negative, so yeah, all the numbers here are negative. And then think of a number greater than 1, like 10. 10 minus 1 is a positive 9, so all the numbers will be positive. Okay, that's a lot of signs there, but let's just see what's happening. So this is for our double prime. So negative and negative is positive times negative. This is negative. This now is, let's be careful with what? This is on the bottom. Right, it's divided by. So if this was a 0 on the bottom, that would be undefined, right? Divided by 0. There's no 0 on the bottom for this factor, so we're okay, but this is a dividing by. So this is going to be 0. Negative times a negative. Okay, positive. Negative times 0 is going to be 0. And then negative times a positive. Okay, so we got these signs. So that means that we have concave down, right, here. We have concave up here, and we have concave down here. So at 1 and negative 1. So that's good. We're getting close here now to putting everything together, right? So if we, I think H is now the sketch, right? This is just the graph now. So if H is the sketch, then let's put everything together. So there's no restriction in the domain. We do have x-intercept and y-intercept is 0, 0, so I'll put that point right there. And again, I'm just going through A, B, and C and jotting down. I know that we have a symmetry about the x-axis, so that's great. There's a horizontal asymptote at y equals 1, right? So we'll put a horizontal dashed line there, which means that as x gets large in both directions, it's going to come approach that line. So because it hits here, obviously it's going to approach the line from underneath on this side, and it's going to approach the line from underneath on this side. So we kind of know that that's what's happening. All right, so it is decreasing up until 0. So it's kind of coming down here. But before we draw that, let's include our, okay, minimum is this, great. So now let's take a look at the concavity. So this is where it's interesting. It's coming down the whole time, but the concavity is negative. So, oh, actually we didn't finish G because we have to know what this point is, right? Sorry, we didn't do POI, points of inflection. So points of inflection are going to be f of negative 1 and f of positive 1, right? Which are negative 1 and 1/4 and positive 1 and 1/4, which I tested 1 and negative 1 for symmetry. So yeah, so if this is 1/4, then that's a point of so it changes from slightly concave down to now slightly concave up. And again, this is not maybe not the greatest. Concave down to flipping to concave up. Then, boom, flipping again to slightly concave down. Okay. And I think that's got everything. So here's your minimum, 0, 0. And this is 1, 1/4, and negative 1, 1/4. And you've got this as y equals 1. Okay? So, how you feeling about that question right now?
I know where I went wrong.
You know where you went wrong? Okay. All right.
Because when the second derivative, I didn't turn into x squared minus 1, I did plus 1.
Oh, really? So literally just a plus instead of a minus? Darn, got it. Okay, well, that happens. That happens. It's a lot of it's a big question, right? So yeah, I get it. That's that happens. All right. So again, tomorrow on your test, you're going to have one of these questions. So roughly half the class will be one of these questions, and then the other half of the class will be some questions about individual things. First derivative test, second derivative intervals of increase, decrease. Limits is x approaches infinity. That's part of this chapter as well. So just little questions like that.